All rocks have stories to tell.
Minerals make up rocks.
There's a lot of minerals that are used in economy, our industry.
Gold, silver, lead, zinc.
And there are also some very beautiful rocks. I love beautiful minerals.
Rocks tell an incredible story. They tell the story of the history of the planet over the last several billion years.
The Earth is made of rock, from the tallest mountains to the floor of the deepest ocean. Geologists study the rocks to learn about our planet and the various processes and events that have taken place.
Scientists read rocks because rocks tell us the history of the Earth. They kind of record the events of the Earth, what's happened over geological time.
I mean, that's the great thing about geology, is that these moments, are recorded in the rock. You can see droplets of rain. You can see dinosaur footprints. In the rock, which is just fascinating. It's more than just recording fossils. It records moments in time.
But before we can understand anything about rocks, we have to understand what minerals are.
The difference between rocks and minerals is that minerals make up rocks. They are essentially the building blocks of rocks.
So the same way that, say, there's a difference between a potato and a stew, right? Because a stew is made up of all these different things, vegetables and broth and potatoes. In the same way, that's the difference between minerals and rocks. Rocks are made up of different kinds of minerals.
Many people are used to hearing the word mineral associated with their jar of daily vitamins. Those are not minerals. Those are chemical elements.
While rocks are made of minerals, minerals are made of chemical elements, essentially atoms such as carbon, iron, or calcium. Currently, we know of at least 113 elements, and at least 92 of these are naturally occurring on Earth. Many are valuable resources.
It's very interesting when you look at all of the resources that we use in everyday life. They're mostly made up of the elements that are in very minor abundances, like the gold in my ring, or any of the metals that we use. For example, if you have a racing bike, it's made out of a titanium alloy. These are all elements that are present in very tiny abundances, and there are various different processes on Earth that have concentrated those elements locally. But if you look at the entire planet, it's really just a few elements that make up most of our globe.
As the Earth formed, many of the heavier elements, such as iron and nickel, were drawn to the center, while lighter elements floated to the top to form the crust. The crust is made up of mainly 8 elements: oxygen, silicon, aluminum, iron, calcium, sodium, potassium, and magnesium.
If we look at the elements that make up the Earth's crust, there's really only 8 elements of the 92 naturally occurring elements that make up the Earth's crust. The 2 most abundant, that make up roughly about 75%, are oxygen being the most abundant at about 46%, and silica. Because those 2 elements are the dominant components of the Earth's crust, logically, they make up the building blocks for about 95% of the minerals we find in the Earth's crust, namely rock-forming minerals.
Rock-forming minerals that contain oxygen and silica are called silicates. Most minerals are usually a combination of 2 or more elements and are represented by the chemical symbol of the combined elements.
So, for example, this is a crystal of the mineral quartz. It's one single grain of quartz. Quartz is a mineral. It has a fixed chemical formula, SiO2, silicon dioxide.
Each of the silicate minerals contains oxygen and silicon, and perhaps 1 or more additional elements, and they make up 3/4 of the Earth's continental crust. However, there are also non-silicate groups, and while they make up only 1/4 of the continental crust, these minerals are used in many important ways, from building materials like cement and drywall to electrical conductors and steel. Some of the non-silicate mineral groups include carbonates, sulfates, halides, oxides, and sulfides. Carbonates include minerals like calcite, also known as calcium carbonate, which is a major component in rocks like marble and limestone, and is also the primary mineral in cave formations.
There are some mineral-type deposits that are more common in caves, your stalactites and stalagmites. That's basically calcium carbonate, but that's what reef rock is made out of. All your limestone, that's calcium carbonate. When you go to places like Yellowstone and you see all the travertine deposits coming out of hot springs, most of that is also calcium carbonate. So they take different forms, but you're still restricted by the same set of minerals.
Sulfates, including gypsum, can also be seen best underground, where they can take on rare and unusual formations.
You do see some more oddball things like the giant gypsum chandeliers. Essentially, they're big selenite needles, and there's very few places, particularly on the surface of the Earth, that you see that, because selenite, which is made up of the same stuff as gypsum, the calcium sulfate, is extremely soluble. This is the same stuff that they make drywall out of. It's very, very soluble in water. So on the surface where you've got rain, you just don't see it. But underground, where you're actually protected by all those layers of rock, you can actually see large displays of very big crystals, and there's very few places in the world that you can actually see those preserved, where you can actually walk by and take a look.
Other non-silicate minerals include halides, such as salt, oxides, like ice and iron, and sulfides, such as ore of copper, as well as native elements, which are called pure elements because they are made from only one element, such as gold and diamonds. A mineral, by definition, must satisfy 5 conditions. 1, it must be naturally occurring. 2, it must be inorganic. 3, it must be a solid element or compound. 4, it must have a definite composition. And 5, it must have a regular internal crystal structure.
So if we take that sort of textbook definition, break it down a little bit, a mineral has to be naturally occurring. So it can't be a man-made thing like cubic zirconium or an industrial diamond or an industrial ruby. It has to be something that's actually made by the earth.
To be inorganic means that it was never alive and cannot be made from plant or animal material.
So if you found a shell is not a rock because it's made organically. But the constituents of that shell, calcium carbonate, those are things that make, there is a calcium carbonate mineral, calcite, that is a mineral, but the shell itself isn't a mineral.
They must be a solid element or compound. So, liquids are not minerals. They must have a definite composition, meaning the chemical analysis of a given mineral will always produce the same ratio of elements. For example, quartz will always have 1 silicon atom for every 2 oxygen atoms.
It has to have a definite set of physical properties and chemical properties. It can't vary in its chemistry too much. Minerals are in essence just chemicals, but they're crystalline chemicals.
They must have a regular internal crystal structure, which means the atoms are arranged in a crystalline structure, in a repeating pattern. Minerals also have certain properties that help us clarify them.
We classify them in terms of things like their hardness, how they break, which is called their cleavage, whether they leave a streak of a different color if you try and write with them on a piece of white ceramic. And all of these different properties that we use to classify them are really telling us about the crystalline arrangement of all of those atoms.
Some of the properties of minerals include crystal form and shape, hardness, cleavage, parting and fracture, color and streak, and luster and transparency. Crystal form refers to the internal orderly arrangements of atoms, but also generally results in a crystal with well-formed faces, like in this quartz grain.
These grew naturally. This is not something anybody cut with a saw, for example. And the crystal faces tell us something about the arrangement of the silicon and oxygen atoms in the crystal lattice for the mineral quartz.
The standard scale for hardness was developed by Friedrich Mohs in 1812 and really reflects the strength of what are called covalent bonds, the chemical link between atoms in the mineral. The standard minerals making up the Mohs scale of hardness are from the softest, talc, to the hardest, diamond, which is the hardest mineral on Earth because of the bonds between the carbon atoms.
Every carbon atom is very, very tightly bonded to every other carbon atom by what are called covalent bonds. And it takes an enormous amount of energy to break those covalent bonds. And because every carbon is connected to every other one by covalent bonds, it gives the mineral its incredible hardness and strength that you just cannot break those bonds very readily.
Because bonding is not always of equal strength in most crystals, some will tend to break.
Where you have a plane of weak bonds, you can break that mineral very easily, and hence it has a very good cleavage. For example, the micas, biotite or muscovite, most kids have probably picked up a book of mica and found they can peel the sheets away. The sheets themselves, again, the bonds are very strong within a sheet, but each sheet is held to the next one by very, very weak bonds, and you can break them with your fingers.
Color also can be highly variable in minerals, depending on various impurities that might get into the crystalline structure. Quartz, for example, can be clear as glass, but it can also be purple, such as amethyst, which you might find in a geode. It can be black, it can be brown, it can be any variety of colors. Pink in rose quartz, for example, or it can be a dull gray, as in smoky quartz. So minerals, depending on, a dash of this and a sprinkling of that, can have a variety of different physical properties and different characters.
Streak, luster, as well as taste or even elasticity and magnetism are all helpful properties when identifying the different and often quite beautiful minerals and valuable gemstones.
Gems are simply minerals that have some special commercial value because of their great beauty and the ability to work with them and cut facets in them, which is enhanced by the orientation of the chemical bonding in those minerals. Certainly some of them have some value other than just as things of beauty. For example, in the computer chip industry and so on, and for making semiconductors and things like that. But as gemstones, really their value is purely how humans place value judgments on them.
A rock is basically a combination of one or more minerals, but it is much more than that. Rocks contain information about the Earth, about the processes that produce them, and the history of the environments that change them. And there are many, many different types of rocks.
What we do to classify a rock is look at its mineral content, look at what type of mineral is in it and how much of it is in it in order to determine what kind of rock is it. And the chemistry of the minerals themselves will depend on how, in what environment they were formed. Whether it was volcanic, whether it was somewhere in the deep sea where there was a lot of water input. These are all things that will determine how those elements will come together.
There are 3 types of rocks. All rocks can be classified in this way. We have igneous rocks, sedimentary and metamorphic. And igneous are like the birth of a rock. They form from magma, which is liquid rock that cools and solidifies and forms an igneous rock. And that can happen underground, or it can happen when they erupt out of a volcano and form lava.
When we talk about igneous rocks, we're talking about a group or family of rocks that contain many, many, many different varieties of igneous rock. But there's 2 main groups we can lump igneous rocks into. We have what are called extrusive or volcanic igneous rocks, and these are igneous rocks that form as a result of lava being extruded on the Earth's surface and cooling and crystallizing very rapidly on the Earth's surface.
And so what happens is that these melts, when they erupt from a volcanic vent, they're so sticky they can't really flow anywhere, and they're so viscous that all of the chemical atoms in them they form into molecules that get tangled up with each other, and they can't make nice crystalline structures. And so it just quenches as is as a glass.
Igneous rocks that cool and crystallize very slowly within the Earth, within the crust of the Earth, are called intrusive or plutonic igneous rocks. And an example of an intrusive igneous rock would be granite.
Granite is the most common form of intrusive igneous rock. The Yosemite area of the Sierra Nevada is mostly all granite, formed deep within the Earth and then exposed later by surface processes like erosion. Sedimentary rocks often start as fragments of existing rocks on the surface of the Earth.
And what happens when it's on the surface is that it's exposed to the elements. It's exposed to water and, all the stuff that's in water. It's exposed to all these chemicals and air, and eventually it erodes, it weathers. So the rock breaks down, its minerals break down, and eventually it gets transported by water to somewhere else. So all that stuff you see in streams and oceans and lakes, you know, that's the sand, the clay, those are bits of broken down rock.
These rock fragments, called sediment, are eventually deposited in lakes, valleys, seas, and oceans. When buried, the sediments lose water and are essentially glued back together.
You can't talk about a sedimentary rock without talking about how it formed, the environment it formed. Was it an ocean? Was it a lake? Was it a river? Was it a desert? Was it, you know, you can't discuss it without really having a good idea of all the elements that came into play in its formation.
They're all formed in a particular environment, a lake, a shallow marine setting near a beach, let's say, or in a stream. And one of the most important parts about studying sedimentary rocks in the ancient Earth is that they can tell us a great deal about what the Earth looked like at that particular time by understanding what the environment was. What was the depositional environment? Was it a swamp? Was it a lake? Was it a stream?
In the sedimentary rock family, there are two main subgroups. There are detrital sedimentary rocks and chemical sedimentary rocks. Detrital sedimentary rocks are formed from the leftover fragments, detritus, of other rocks.
There's mudstone, you know, there's sandstone. Those names come from the size of the clasts in a rock.
A class refers to the size of the rock particle in different detrital sedimentary rocks.
So, for example, the detrital sedimentary rock conglomerate are made of fragments that are 2 millimeters or greater in size. Sand are fragments that range in size between 1/16 and about 2 millimeters in size. Silt ranges in size from about 1/16 to 1/256 of a millimeter, and clays are really tiny. That's anything less than about 1/256 of a millimeter. So, detrital sedimentary rocks are based and classified by grain size.
The other thing to remember about sedimentary rocks is that there's a part of them which are not formed by the detritus, the eroded material of other rocks, but are formed by biochemical and chemical means. And these are very important sets of rocks, especially our carbonates, our limestones. And most of those are formed indirectly or directly from life, from the hard parts of various forms of life, from shells on the beach to various kinds of plants that have essentially spines of hard skeletal parts, to bones from vertebrates. And any of those things that accumulate in layers or are mixed with detritus give us a kind of sedimentary rock that is formed fundamentally by biological remains.
And usually it's the mineral composition which will identify it. For example, calcium carbonate rocks made of this particular mineral are usually called limestone. Rocks made of the mineral halite, which is common table salt, are what are called evaporites. And because they're made chemically, they fall under the subgroup of chemical sedimentary rocks.
Metamorphic rocks are also formed by the modification of a pre-existing rock, but this time by heat and pressure on the rock.
If we take that rock now and we bury it very deeply, maybe we take it down a subduction zone, or we slam two continents into each other and we bury the rocks and heat them up. This is the process that forms metamorphic rocks.
Those pressures and temperatures eventually, you know, if you're deep enough in the earth, cause the rock to change again, causes the chemistry to kind of want to rearrange itself to accommodate to those temperatures and pressures. And that's what happens when the minerals are pushed upon, basically. I mean, they're literally just pressure pushes upon them until they rotate in a preferred direction.
This process causes many changes in the rock, including a change in density, growth of larger crystals, and the transformation of low-temperature minerals into high-temperature minerals. These metamorphic rocks are then divided into two groups, foliated and non-foliated.
So metamorphic rocks actually go through gradations depending on the type of metamorphic rock. Foliated metamorphic rocks, which usually start out as a clay-rich shale, will go from low grade to high grade. An example of a low-grade metamorphic rock would be slate. Just like you go down and buy slate tile at the hardware store and tile your floor with it. Non-foliated metamorphic rocks include things like marble. If you take the chemical sedimentary rock limestone, and subject that to heat and pressure, you'll form marble, which most people know is a rock used in architectural or artistic enterprises.
Rocks on the Earth's surface vary in age, from less than 1 million years old to over 3 billion, but all are much younger than the 4.6 billion-year-old Earth. The reason rocks are younger than the Earth is because they are recycled. From igneous to sedimentary to metamorphic and back again, the Earth's rocks and minerals change over and over in different environments in what we call the rock cycle.
The rock cycle is a representation of how dynamic the Earth is, really. Rocks are in a constant state of change, a constant state of flux.
So this igneous rock was on the surface, it gets broken down into sediment. Sediment gets washed into an ocean or a lake, and there it forms a sedimentary rock. And then it gets metamorphosed, and then eventually it's buried deep enough, it gets turned back into magma, and then it comes back again. So that's what we refer to as the rock cycle. So these same elements, these same oxygens and silicas and carbons get put into this cycle and get reformed and put back in and reformed.
To us as humans, we think rocks are immutable. They're not going anywhere. They're here forever. But indeed, rocks are always changing. Rocks are eroding to become sedimentary rocks, or rocks are being heated and changed to become metamorphic rocks, or rocks are being melted and recrystallized to become igneous rocks. The rock cycle is a representation of this dynamic nature, of Earth's dynamic nature.
The Earth's crust is very thin compared to the rest of the Earth, but it contains the rocks and minerals, providing us invaluable resources for economy, recreation, and information about the intricate history of our planet Earth.